Welcome to 3A03, week 8, Tuesday. The agenda for today, we're going to go into shearing stress for now thin wall analysis. Okay, so we have done non-thin wall last week. This week, we're going to focus on thin wall analysis. Just an early reminder, we have term test 2 coming June 29 from 7 to 9:30 p.m. Location to be announced. You're going to get 3 questions. Questions will be very similar to homework 4, homework 5, and homework 6. Okay, so you have to be able to do homework 4, 5, and 6 to do term test 2. Right. So we are going to now look into shearing stress. Okay. Shearing stresses in thin wall. Has 2 configuration. And 1A, the first one, is known as a box beam. And B is a wide flange. Okay, and I'm going to show you the difference. And in the test, okay, or during, I'll put here note to in term test 2. Okay, term test 2, in case some of you are curious. The question will specify whether to use thin wall or non-thin wall analysis. Okay. In real life, you have to more or less make a judgment, or you have to do both. Okay, but now, as I said, this is the first time you're looking at it. Okay, so term test 2, the question I will tell you whether to use thin wall or not to use thin wall analysis. Okay, so let's specify what do we mean by box beam. And I'll give us a bit of space and what we mean by wide flange. Okay, so I've attached these figures on Avenue to Learn, which you can copy. Okay, so as you can see, this is a box beam analysis, and what you can see over here, this is a wide flange analysis. 2 very distinctly different structure. Okay, and I'll tell you why is it different. But before I carry on, I go any further, again, in this topic, there are only 2 equations to use. Okay, so the equation we're going to use is shear stress is equal to VQ over IT, which you're very familiar. And then small q is equal to VQ over I. Same formula. Okay. The difficulty part is how to find the first moment of area. The first moment of area Q is always the problem. Okay. So over here, right? So what we tend to call the vertical section, right? If you see any vertical section over here, these are the vertical section. And this is what we call the major web. Okay. So what do I mean by major web? So the major web, okay, so before I go any further, all these arrows, small arrows you see are known as your shear flow Q, right? So all these arrows you see, you got Q1, Q2, they are known as your shear flow. So the shear flow Q, right, is similar to fluid flow. Okay, so it's like how fluid is flowing. Okay, now one thing I want you to take note is going to be there's another rule I'm going to specify. I know we have 5 rules already. Then this is rule number 6. Okay, rule number 6 is the major web controls the direction of the shear flow Q. Okay, so what do I mean by that? Okay, so as you can see, if we were to look at box beam, right? So I'm going to highlight the major web. These are known as the major web. Okay, this is the major web. This is also the major web. Okay, so the major web is controlling the shear flow direction. Okay, so you can see that over here, right, is a continuous one direction shear flow from the top to bottom, okay, of the structure, right? So the major web, you can see is a continuous flow of shear flow Q. And it's also very similar, okay, very similar to what you see over here, where is the white flange, right? The shear flow is a continuous motion from the top to the bottom of the structure. So that is how you design your shear flow. Okay. Later on, I'll come to an example. And then I want you to look at the box beam on the left. On the box beam, point A and point B, you can see these points over here, or box beam analysis, right? These are known as terminal. So this is terminal 1, and this is terminal 2. And I'm going to write rule number 7 is the shear flow at shear flow Q at the terminus is equal to 0. Now, you can see, let's look at the left-hand side, the box beam, all right? You have 2 terminal, terminal 1 and terminal 2. Why we call the box beam? Because it looks like a box, okay? And for a box beam, right, if we look at the top of the centroid and at the bottom of the centroid, you see the terminal at the top, right, it branch out 2 Qs, okay, Q on the left and then Q going towards the right, okay. And at the bottom, right, it ends up in the same terminal, which is terminal 2 at point E. Okay, so for box beam, they start from the same terminal at the top of the centroid. They end up in the same terminal on the bottom of the centroid. Okay. Okay. So let me quickly refresh. Number 1, thing that we have to remember: the web controls the shear flow, the direction of the shear flow. continuously from the top to the bottom. It's like the expressway. Okay. Now, for the box beam, if at the terminal, which the shear flow is equal to 0, right? At the top of the box beam, right? The shear flow one flow from the to the left, and then flow from the right. They start from the same terminal. And then at the bottom, they end in the what? Same terminal. Okay. So one thing I also like to highlight is I like to one thing. Go on. I cannot remember what I want to tell you now. Oh no. So one thing yeah, I want to highlight is at the terminus the shear stress is, or the shear flow is equal. Oh, I remember what. Over here you can see that the length of Q is related to its magnitude. Okay, the longer that arrow means the higher the Q value. Like over here, the Q value, the arrow is so short, means the Q value is getting smaller. Okay, then at the terminal, there's no Q value. Okay, now that is for box beam. Now, if we look on the right hand side, which is known as a white flange, what is very interesting is, so this is our centroid. And that's our top, and this is our bottom. What we realize at the top, we have two terminals, one known as T1, the other one known as T2. Okay, so for a white flange at the top, you have two terminals. You have one terminal on the left hand side and one terminal on the right hand side of the flange. Okay, then it combines together at the web, and then if you look at the bottom, it ends off in two separate terminals again. One of it ended up in T3, terminal 3, the other one ended up in terminal 4. Okay. Now later on, I'll show you how does this terminal play an effect into your analysis. But you have to remember this. At the terminal, okay, the shear flow is equal to 0. Okay. Then there's another new rule that I'm going to incorporate. So rule number 8. Okay, rule number 8 is the walk thickness orientation. Okay, the wall thickness orientation is always perpendicular to the shear flow direction. Okay, so you will say, Eugene, what do we mean by that? Okay, so I'm going to look at box beam. Okay, so let's look at the box beam. Right. So if we look at the box beam, right, all these pink arrows are your shear flow. Okay, so for the box, let's say if I want to find at a point alpha, right, I want to find the shear stress. This is the thickness. Okay, if I want to find the shear stress at point beta, which is at the centroid, this is going to be our thickness. Okay, so that's for box beam. For the white flange, same thing applies. If we want to find the shear flow of point alpha over here, right? The thickness to be taken is this thickness over here, and at point beta, which is at the centroid, this is the thickness that you take. So what you realize is the thickness is always perpendicular to the what? The thickness is always perpendicular to the shear flow. Okay, so these are the things that I want you all to get used to it. Okay, so now we are going to first design some shear flow first. Okay, so I like to do difficult problems. Okay. Oh, okay. So let's look at this one. Right. So you can see like, whoa, this is pretty complex, right? This is pretty complex. So the first thing we're going to do, we're going to identify that this is our what? Major